Hello, everybody. Get my stuff together. Go. Chat. Okay. There's the attendance form. Go fill it out as usual. Wait a minute here. Let's see. So I'm guessing today we should talk more about double integrals, and we should also continue talking about linear systems of differential equations. Does that sound good, or is there something else you guys want to be hearing about? Let's see here. All right, well, I'll do a few more double integral examples, and then we'll continue talking about linear systems of differential equations, because what I imagine we're doing, and again, it's going to be hard to know exactly because this is the first quarter of 17C using the new textbook, so it's not super clear exactly which direction they're going to go with things, but we'll continue talking about differential equations and kind of classifying the equilibria of the solutions, classifying the solutions to equilibria. Excuse me, classifying the solutions to the differential equation and seeing if they're stable or unstable, or yeah, that's it. So kind of like we did in 17A, right? When we did like the, you guys kind of remember, so let me actually, let's do some double integrals. Then I'll kind of take you back to 17A for a second, and then we'll continue on with 17C. Pen should be good, all right. So I've got some examples here. You seem good. Sure. You seem less exciting. Let's start off with a fun one. Let's do this integral. Integral from 0 to 2, and then from 0 to 4 minus x squared. What do I got here? X e to the 2y divided by 4 minus y and dy dx. By the way, before I even finish writing this integral, you should know it's dy dx, because the inner limit has the variable x, the inner integral has to be with respect to y. Right? If we were going to integrate this, we would integrate with respect to y. We would do stuff with the y's, and then we would plug in y equals 0 and y equals 4 minus x squared, except in the other order. So once you see this variable here, we know the opposite variable is the one we're integrating with respect to first. Okay. Now, obviously, this is terrible, right? Ignoring the x, I don't know how to integrate e to the 2y over 4 minus y. And the whole point of problems like this is if it looks terrible, you're meant to change the order of integration. It's the whole idea. So I'm going to graph this region here. And again, you don't have to, right? You don't have to graph it by hand. You can use Desmos. You can totally graph this on Desmos, but we can also graph it by hand. So let's see, we've got y equals 4 minus x squared. I've got y equals 0. I've got x equals 0, and this point here is x equals 2. So I'm looking at this region here. And at least the way it's currently being written, it's being imagined where you've got these, vertical strips. right? So the y is going from 0 to this function, and then the strips are going as far left as x equals 0 and as far right as x equals 2. But of course, we're going to change the order of integration. Also, here's the attendance again in case you need it. So we're going to reimagine this using horizontal strips that are going to be bounded on the right by this function and on the left by this function. So starting to write the double integral for dx dy, I know my inner limits of integration are going to go from x equals 0 to whatever this function is, but as a function of x, or sorry, as a function of y, where x is a function of y. So I have to solve this for x. So let's see, I'm going to get x squared equals 4 minus y. And then when I take the square root, I don't just get the square root. What do I actually also get? So I get, what am I missing from that x equal to the square root of 4 minus y?
Plus or minus.
Exactly, yeah. Now here's the thing. Plus or minus is actually kind of a red herring, right? We don't want the plus or minus because the plus is one side and the minus is the other side. So just make sure you're careful, right? We clearly want the plus side because here x is positive, so we want x to be the positive square root of 4 minus y. But if for some reason they had described, this other region over here, then you would want the negative square root of 4 minus y. So just make sure you know which region you want. So we want the positive square root of 4 minus y. And then these black strips are going to go as low as y equals 0 and as high as y equals 4, right? Because we're going to draw more strips, more strips, more strips, all the way up to y equals 4. With the same terrible looking integrand. Okay, but then this is relatively not terrible because really I'm thinking of this as x times e to the 2y over 4 minus y. Right, and if I'm integrating with respect to x, well, that's super easy. I've got a constant times x. The integral is the constant times x squared over 2. So I'm going to get the integral from 0 to 4. Integrating this, I'm going to get x squared over 2 times that from 0 to the square root of 4 minus y. All right, I can bring out the 1/2. And then plugging in the square root of 4 minus y, I'm exactly going to get the 4 minus y. So this actually works out perfectly, right? This part here becomes square root of 4 minus y, square root of 4 minus y, times e to the 2y over 4 minus y, minus 0, right? So I plugged in 0, I get 0 here. And then this is just nice, right? Those cancel. And so then you're left with, let's see, 1/2 the integral from 0 to 4 of e to the 2y dy, which is super not terrible at all. We anti-differentiate this, we get another division by 2. So we actually get 1/4 e to the 2y from 0 to 4. And plugging in, sorry, I'm like going backwards here. Plugging in, we get 1/4 e to the 2 times 4 is 8 minus 1/4 e to the 0, which is just 1. So that would be our final answer. So that's an example of how these problems can start off looking terrible, but actually end up being not that bad as soon as you change the order of integration. Let's do at least one more. Let's see what I got here. Yeah, that's not too terrible. Okay. That one or that one? Sure, let's try this one. Integral from 0 to 3, integral from the square root of y over 3 to 1 of e to the x cubed dx dy. And again, it should be moderately straightforward, moderately obvious that we can't do it this way. Right? E to the x cubed, we do not have, we're not able to integrate. It's not that we don't know how, so we're not able to. No one's able to. So this problem, as it stands, can't be done. So we need to re-express the integral as something, something, e to the x cubed, dy dx. So we have to change the order. So here's what I want you guys to do. I want you to draw this region. So I want you to draw the curve. So first you're going to draw, x equals the square root of y over 3 and x equals 1. Draw both of those on your own. It's not my best. So here's my question for you guys. Does this x equal the square root of y minus 3? Does it look like this? Or does it look like this? Does it look like a square root or does it look like a parabola?
Is it parabola?
Yeah, it does look like a parabola because, right, if we solve for y, we end up getting x squared equal to y over 3, and then y equal to 3x squared. So yeah, we can see that it should, parabolas and square roots are kind of the same function, just depending on the way, the orientation you're looking at them. But this one, with the usual orientation, looks like the parabola, like the upward opening parabola. And this point of intersection here is going to be, well, it's going to be an x equals 1. So if we plug in 1 for x, we're going to get y equal to 3 times 1 squared, which is 3. So this point here where they intersect should be the point 1 comma 3. Which is nice because, so usually the region they're describing with limits of integration shouldn't be cut off weirdly. Like it'd be weird if it was y going from 0 to 2, right? If we had if we stopped there and just had this region, that would be kind of strange if we stopped at 2 right, instead of 3. Usually you've got the entire area that's being enclosed by the intersection of whatever functions you're looking at, typically. Okay, so we've already done most of the work actually to change things around. In our original expression, we had horizontal strips, right? This was going from x equal to the square root of y over 3 to x equal to 1. And then our strips are ranging as low as 0, as high as 3. Now we're going to draw a vertical strip. It's going to be bounded below by y equals 0 and above by y equals 3x squared. And then that vertical strip can range or slide as far left as 0, as far right as 1. And that's how we would do that. And so then the rest of it's not too terrible. Sorry, this is y equals 3x squared. So integrating this with respect to y, we just slap on a y. Right, we get the from 0 to 1 of y times e to the x cubed from 0 to 3x squared dx. And then we plug in the 3x squared for y and the 0 for y. We get the integral from 0 to 1 of 3x squared e to the x cubed minus 0 times e to the x cubed, which I'm not going to write. And hopefully you guys can see, you can probably do this without even doing the u substitution. Right? U is equal to x cubed du is exactly 3x squared dx. So this is really just, right, this is the integral. This really is my e to the u du, whose integral is just e to the u. So this ends up being e to the x cubed from 0 to 1. And because the derivative of e to the x cubed is e to the x cubed times 3x squared, which is exactly that. So end up with e to the 1 minus e to the 0, which is e minus 1. If you see a really obvious u substitution like that, sorry, my hair is driving me crazy here. Oh. I'm always on the wrong side of the camera for my face. I'm like, no, not that side, this side. But that's not the way you should stand. Okay. Sorry, off topic. If you see a really obvious u substitution like this, you can show as much or as little work as you need to. Are there questions about this? I'm erasing this. All right. I think it's probably worth our, so certainly happy to do more of these later, but I think we should continue moving in the direction of where this thing should be going, which is talking about solutions to linear systems of differential equations. Before I do that, I want to remind you kind of just some examples we might have done in 17A. So I'm going to pick one that's pretty easy. Yeah. So you might remember we had differential equations in 17A that might have looked something like this. dn dt equals, let's make it super simple, James. 2 minus n times 5 minus n. It might have been unfactored, but I think we did stuff like this before. And we said, okay, well, we have some equilibria. And because this dn dt means the rate that n is changing with respect to time. And if we're saying we're looking for an equilibrium point, we're looking where the rate of change is 0, right? The equilibria are where things aren't changing. So the equilibria here are when the population n is either equal to 2 or when n is equal to 5. Right? They're just the solutions to setting the derivative equal to 0. Or the differential equation equal to 0. Now, graphically, we can actually see which of these is stable and which of these is unstable. So I'm going to graph, and so the graph isn't going to be n as a function of t. The graph is going to be on the x-axis. I have n, the population at time t, or n of t if you like. And on the y-axis, I have dn dt, the derivative. Basically, I'm just graphing this parabola, right? My x's are now n's, and my y's are now the whole function here. So I graph this. It's got intercepts at 2 and 5. And it's a what? Okay, n squared. Sorry, it's an upward opening parabola, right? So it looks kind of like this. Looks kind of, but not quite. A little bit better. Sure, that's 2. You could pretend. Okay. And the way we saw before, if 2 or 5 were stable or unstable, we're to think about, well, what does it mean that the derivative is doing? So over here, right, between 0 and 2, the y values, the dn dt values are positive. If dn dt is positive, that means n is getting bigger. So in here between 0 and 2, n is getting bigger. Between 2 and 5, dn dt is negative, right? The y values are negative, which means n is getting smaller, right? If your derivative is negative, your variable or your thing is getting smaller. So we're going that way. And then over here, again, dn dt is positive, so n is increasing. So here's what we can say. 2 is a stable equilibrium, because if you perturb a little, on either side, right? If you move off of 2 a little bit, these arrows will push you back towards 2. To contrast that, 5 is not stable, right? If you are not at 5, right? If you're a little bit to the right of 5, the arrows are going to push you away from 5. If you go to the left, the arrows are going to push you away from 5. So 5 is an unstable equilibrium. 2 is a stable equilibrium. And that's kind of where we're going eventually with what we're about to talk about. But it's a little bit more complicated because we've got multiple variables. But the idea that we're moving towards is classifying the equilibria of, sorry, there's a lot of words. When we find these solutions to, well, God, we're going to classify the equilibrium points. Okay, so let's see, how do I want to do this? So I kind of want to, I'm going to share my screen for a minute here because I think I got some stuff that's worthwhile. Also, here's the attendance again, just in case you didn't get it yet. So let's see here. I want this up. Okay, 1 second. All right, sharing the screen. Okay, so I'm just looking at some handouts from Grant's webpage, actually. They're from his 17C his old 17C stuff, but it's still viable. I mean, this is actually this is the example we've been doing a little bit of. So we were solving this differential equation, dx1 dt equals x1 plus 3x2, and dx2 dt equals 2x1 plus 2x2. And there's also some initial conditions here, which we'll talk about in a minute. We found the matrix. We then found the eigenvectors and eigenvalues. It was a bit of work. We found the eigenvalues to be 4, -1. We found the eigenvectors to be 1, 1, and 3, -2. And so we've definitely done that. And then we even talked about how we could write the solution as C1e to the lambda 1t times V1 plus C2e to the lambda 2t times V2. And that, so I wish I could like highlight this. I can't highlight it because I'm not well equipped in that one. But this right here, that's the general solution to this original differential equation, which I'm going to write up here just so we guys have it. So the original, it was right, dx1 dt was equal to, I forgot what it was. Of course I forgot what it was. 1x1 plus 3x2. And dx2 dt is equal to 2x1 plus 2x2. Now, before we get going further, I want to point out that 0, 0 is definitely an equilibrium point. Because if x1 is 0 and x2 is 0, then the derivative is 0. And if x1 is 0 and x2 is 0, then this derivative is 0. And if both derivatives are 0, nothing is changing, and you're at a point of equilibrium. So again, the equilibrium point are just where both of these derivatives are equal to 0. So looking back at this, there's some work here about solving for the constant C1 and C2, which we did talk about. But here's what I really wanted to get to. So if you look at this equation here, you can actually find a direction field for it. Now, graphing a direction field is a real pain in the butt. And I feel like we might have talked about this in 17B a little bit. Is that right? Did we talk about direction fields in 17B? Okay. We don't want to graph them, right? It's terrible. It takes forever to plot points. And here's the great thing. You don't have to. So there is this, and maybe you know about this already. There's this thing called p-plane, phase plane, which if you Google, I believe it is, oh God, what did Sarah tell me to say? Let me look real quick here. If you look up p-plane, Rice University, and if you click on that, you can download the p-plane one. I think is the one that is actually easier to do, like 2 differential equations at once. I was looking at the D-field one, and I feel like you can only do one differential equation. So here's the p-plane one, and where's the other little part of it here? Sorry, there's another part I need there. There's the other part. So you can actually enter the differential equation. So I'm using x for x1 and y for x2. And I've got x prime, right? That's what that little prime there, so that's dx1 dt equals x1 plus 3x2, or x plus 3y, and dy dt, or dx2 dt, is 2x plus 2y, or 2x1 plus 2x2. And then if we click on the little thing to graph it, well, it's already there, sorry. So it gives you all of these little things, but you can also click on it. And when you click on it, it'll tell you the behavior if you have a particular initial condition. So if we look back, sorry, I'm gonna go back over here. So if we look back over here at the initial condition of, sorry, x1 equal to 0, sorry, x1 at 0 equal to 2, and x2 at 0 equal to 1, or basically x equals 2 and y equals 1. We can go over to this, we can go over to, let's see, x equal to 2 and y equal to, sorry, I said 1, but I didn't say -1. So I go over here to the point 2, -1, I can click on it, and it will show me what the what the curve through that particular point looks like. And if we had a different initial condition, right, like something over here, like, I don't know, 0, -2, it'll show you what that looks like, which is kind of useful. It also shows us something interesting. So if we go over here and look at 0, 0 for a second, 0, 0 is kind of funky. I wonder if I can click like a little bit above it too. So 0, 0, not surprisingly, is where if you're going through 0, 0, you're on one of these paths that is the eigenvector. So if I look back at my eigenvectors for a second, my eigenvectors are 1, 1. And look, this line here is exactly the line that the eigenvector 1, 1 goes through, right? From here to here, it goes over 1 and up 1. That's the vector 1, 1. So, and similarly, this eigenvector 3, -2, if I go from this point over 3 and down 2, I'm exactly there. So the eigenvectors or eigenlines go through the origin because the origin is the equilibrium point, and these will always go through it. What was I going to say here? There's something else I want to say. Yeah, we should look back at this. So there's more to say. Yeah, sorry, there's a thing. So here's what I want to say. So this is what our general solution looks like to this equation that goes through this point here at 2, -1. Or I should say our particular solution, not our general solution. So the solution is x1 of t, right? And it's not like super meaningful, right? I'm like, okay, big deal, right? I've got x1 is 3/5 e to the 4t plus 3/5 e to the -t, and x2 is 3/5, right? But the thing to know about this is that if your eigenvalue is negative, it eventually isn't going to contribute in the long run, right? So the negative, right, the coefficients of t are the eigenvalues. So here's my eigenvalue of 4, here's my eigenvalue of -1. And as time goes on, right, as we let things progress, this e to the -t is going to get very, very small, because if t gets really, really large, right, e to a negative big number is like 1 over e to the big thing, right? So this part ends up not contributing, and this is the thing that kind of informs us about what our solution actually looks like in the long term. And even more generally, so if one is positive and one's negative, it's the positive one that's always going to take over. If they're both positive, I think, I don't remember, I'll have to remember, I think it's the more positive one. And if they're both negative, they both kind of, eventually both things go to 0. So here's what I want you to see right now. This point here, this equilibrium point 0, 0, if you travel on this eigenvector, right, you'll actually end up at the equilibrium point. Kind of like how if you start at the equilibrium point here, you won't move, even though it's unstable. Right? If you actually started at, right, if n was equal to 5, you would plug it in and d and dt would be 0, so you would just stay at 5. But if you're just a little bit off, right, like if n was 6, then d and dt is going to be -4 times -1, which is 4. And then the rate of change of n is 4, and so you move further and further away. The same kind of thing is true here. If you're on this line that actually goes through the equilibrium that's 0, 0, you'll actually end up there. And the same kind of thing here, right? If you started at 0, 0, you would just stay there. But if you're over here a little bit, right, these arrows are pushing you away from the equilibrium. And these arrows are pushing you away from the equilibrium. And that corresponds to the positive eigenvalue, right? So the positive eigenvalue is pushing you away from the equilibrium point. The negative eigenvalue is pushing you in towards the equilibrium point. Some more I want to say about that. Kind of. Okay. So I see. So the thing I want to say is, depending on what your initial condition is, you might end up at the equilibrium or not, right? If your initial condition was the point 2, -1, like it was here, well, you get pushed way in this direction of this eigenvector dominating and this eigenvector not being meaningful at all. But if you actually start at the point, 1.5, -1, that'll actually get you back towards the origin because you're already on that line of stability. Let's do another example. And let me see. I'll stop sharing your screen. We'll come back to this though, because I think that's a useful tool to use. I encourage you all to take advantage of it. I think it's not too terrible. It's certainly better than trying to actually draw a direction field. So let's look at a second example here. Is this the one I want? Not really. Sorry, just one second. We can look at this one too, I guess. I want to look at this other one. Cool. Yeah, here we go. Okay. So let's say, also, by the way, I will certainly, I haven't graded your guys' quizzes yet, but I have written solutions to the quizzes. So I'll post the solutions and then I'll try and get the quizzes actually graded sometime today or tomorrow so you can see how it's going. But let's look at this system of differential equations where dx1 dt is equal to -2, and actually, -2x. I'm going to use dx and dy. Either way is fine. You can use x1 and x2. You can use x and y. It's kind of the same thing. dy dt is going to equal, what do we got here? 3x minus y. And I want to go ahead and find the solutions to the system of differential equations. And so I just want to mention, because it's always true, for a linear system of differential equations like this, 0, 0 is always going to be one of the equilibrium points, right? If you plug in 0 for x and 0 for y, all these things equal 0. So whenever you have something like dx dt is ax plus by, and dy dt is cx plus dy, that's always going to have 0, 0 as an equilibrium. You can have other equilibria. I think you can have other equilibria. Now I'm not so sure, but definitely 0, 0. I think to have other equilibria, you actually have to have something more complicated. So I think these linear systems only have 0, 0 as the equilibrium point. You have to have something more complicated to have other equilibria. All right, so we're going to solve this. We're going to write the matrix. The matrix is -2, 0, 3, -1. Now, the nice thing about this matrix, and this was definitely on the quiz, is that you don't have to do any work to know what the eigenvalues are. If you have a matrix that's upper triangular, not like this one, or lower triangular like this one, where the things, so upper triangular just means everything below the main diagonal is 0, and lower triangular like this one, this is lower triangular, just means everything below the main diagonal is, or everything above the main diagonal is 0. When you have that, and you have a 0 up here or a 0 down there or both, your eigenvalues are just the diagonal entries. So I'm going to say lambda 1 is, I guess I would say lambda 1, even though they're out of order, I would probably say lambda 1 is -1 and lambda 2 is -2. It seems like it'd be funny to write lambda 1 equals -2 and vice versa. And that's just because, right, if we solve this equation, right, -2 minus lambda times -1 minus lambda minus 0 times 3, that 0 there or 0 there makes this part not matter. and you just get this product equal to 0, meaning lambda is going to be -2 or -1. So that's why that always ends up working out that way. All right, let's find the eigenvectors. Okay, so for lambda 1 equals -1, I've got the matrix times the eigenvector that I'm about to find equal to -1 times the eigenvector that I'm about to find. And using the first equation, I get -2 times x equal to -1 times x. Okay, if -2x is equal to -1x, what does x have to be? Anybody? Anybody? Okay, I didn't see that. Thanks. Yeah, definitely 0. Right, if you have a multiple of x equal to another multiple of x, the only thing x can be is 0. You can also add 2x, right? But once you see this, like 3x equals 5x or 2x equals 7x, you know x has to be 0. And once you know one of them is 0, you automatically get to say that the other one is whatever you want it to be that's not 0. I'm going to pick 1. You're going to pick 1. We're all going to pick 1. So the eigenvector here is 0, 1. All right, let's do it for lambda 2. So lambda 2 is -2, same sort of thing. -2, 0, 3, -1 times xy equals -2 times xy. Now, I will say, normally I would stick to using the first equation, but I can see it's not going to help. Because -2 times x plus 0 times y equal to -2 times x is true. It's definitely true that -2x equals -2x. It doesn't tell me anything, right? X could still be anything. So that's why I'm going to use the other equation. So I'm going to do 3 times x minus y equal to -2y. And I'm going to add y to both sides. So 3x equals -y. And I'm just going to pick values. I'm going to pick x equal to 1. If x is 1, -y equals 3, so y equals -3. So the eigenvector here would be 1, -3. Okay. And so then writing our solution, our general solution is that xy. So you should be more careful than I'm being here. This xy is not the same as this xy. I was just kind of, I mean, maybe I should use like u and w or something instead of x and y. I was just using these to help me solve for the eigenvectors. So don't confuse this xy with this xy. This xy are the solutions to this differential equation. So xy is equal to c1e to the lambda 1 t v1 plus c2 e to the lambda 2 t v2, which just ends up being c1 e to the, let's see, lambda 1 is -1, negative t, times v1, which is, where'd you go? 0, 1, plus c2, which we still don't know, e to the lambda 2t, which is -2t, v2, which was 1, -3. And we could certainly give ourselves initial conditions if we wanted to find C1 and C2, but that's usually less of what we're interested in. We're more interested in, okay, what does this general solution mean about my equilibrium? Is my equilibrium stable or unstable, or maybe it's a saddle? So actually, I should mention the previous problem, the equilibrium was a saddle, which is usually unstable. If you think about a saddle, like an actual saddle, if you graph it, right? If you're kind of on this line, you're stable, but as soon as you move to either side, you're going to kind of like roll down the hill. So I think that's how I think of saddles being unstable. Whereas a minimum, right, kind of like a paraboloid opening upwards, you can think of as being stable, and a maximum, a parabola opening downwards, you think of being unstable, because again, if you're at the top, if you move in any direction a little bit off, you're gonna like roll down the hill. So in this case, so actually let me go back to, let me share my screen. So we look back at this one. This one's definitely a saddle, because one direction is pushing you away from the equilibrium point and one direction is pushing you towards the equilibrium point. Let's go ahead and look at this system that we just looked at. So I'm going to rewrite my system. It's going to be dx dt equals -2x, and dy dt is 3x minus y. And yeah, that should be good enough. So I look at this, and then again, if I look at my origin here, there's the 0, 0 point right there. It looks like things are swirling in towards it, and they are. I can also, so if I look at my, how do I say this right away? So if I look at any random point, right, like right, let's say I pick right there. If I start there, it looks like it's definitely pushing me towards the origin, right? Same deal if I start over here. Whoa, I didn't, you know, was that always going to connect with that? Okay, sure. So right, all points seem to lead to the origin. So this seems to be what we would call, what's the word I'm looking for? A sink or a stable equilibrium, right? The sink is everything's kind of pushing into it, like draining down the drain. Specifically, if you look at the eigenvectors, which was 0, 1, and 1, -3. So if you pick some point of travel that was in the eigenvector direction 0, 1, so 0 in the x direction and something in the y direction. So I just go up to the point like 0, 1. Actually, let's go down. Right, you can go any, right? When you're on the eigenvector, that's when your travel is a straight line. You're just traveling along the eigenvector. And again, it's pushing us towards the origin. We can also look at the eigenvector 1, -3, right? Right. Yeah, 1, -3. And so if I go from 0, 0, if I go over 1 or over a half and down 3 halves, if I start there, it should also point me straight to the origin. Whereas other starting points are going to kind of loop around and, you know, get pushed by kind of both things. But if you're just starting on one of the eigenvectors, then you're kind of ignoring the other one. Now, looking at the equation, what's happening here is that as t gets very, very large, e to the -t gets very, very small. So does e to the -2t. So no matter what values we start at for x and y, once you start letting t get larger and larger and larger, both of these values get smaller and smaller and smaller. And this thing times everything else being super duper small is going to make this just 0 plus 0. So no matter where we start here, since both of our eigenvalues were negative, we have a stable equilibrium. And so the takeaway here, the general takeaway, is that if both your eigenvalues are negative, you have a stable equilibrium. If both your eigenvalues are positive, you have an unstable equilibrium. And if both of them are of their opposite signs, you have a saddle like we had in the previous example. So let me actually, so I don't think I have time to work through more, but let me show you another one here. Where'd you go? So actually, yeah, look at this. Yeah.
James, can you?
Yeah.
So you said that for the signs, if both are negative, they're stable. If one's negative, one's positive, it's saddle. And if it's both positive, it's unstable.
Yeah, and specifically, it's called a source.
The source.
So like just how like a sink, everything is pointing in towards it. A source, everything is pointing out away from it, right? You're the source, and everything is emanating from you. So let me actually, I think I have an example of that here.
And that refers to the eigenvectors or to which
It
part?
refers to the signs of the eigenvalues. So if both eigenvalues are negative, like in this example, we have a sink, right? Everything is pointing in towards the origin. If the eigenvalues are opposite signs, we have a saddle, where one direction things are pointing in towards the center, and one direction things are pointing out. And then we haven't seen yet, which I'm trying to look for an example of, is where you have both eigenvalues being positive. I'm sure I can make something. I could definitely make something up that's not too hard. I just have to think for a second here. Let's see. Let's do this. Sure, I'm just going to change it up. 3x and -x plus 2y. Sure. So this, I'm just using the fact that, right, so my matrix here, would be the matrix 3, 0, negative 1, 2. And it obviously has 3 and 2 as eigenvalues. So if I graph this one, we can see that, look, everything is pointing out from the origin. If I look at the origin here, right, everything is moving away from it. I was trying to do that. So see, I don't know what my eigenvectors are because I didn't find them, but anywhere we start, we're just going to keep moving away from the origin. And this is called a sink. It's kind of fun, I'm not going to lie. So yes, everything is pointing away. So both eigenvalues positive, you have a source. Sorry, I said sink, I meant source. Both eigenvalues positive, you have a source. Both eigenvalues negative, you have a sink. And opposite signs, you have a saddle, which we usually classify as being unstable unless you're on the eigenvector that has the negative eigenvalue. So going back to our first example, not you. Going back to this example, y. In fact, Grant has actually written this on here. So I'll also mention Grant's materials are useful. I definitely crib from them all the time. You guys are welcome to as well. So if we look at this example again, where it was a saddle, right? We have like this kind of deal going on, right? And then same kind of stuff over here, right? Where you're traveling, if you're starting here, you're traveling this way, but then you're getting pushed way over there, or you're getting pushed over there. So, right, if you're not on the eigenvector that actually takes you to the origin, you're unstable, or you're going to get pushed away from the origin. But if you happen to luck out and actually be on the eigenvector, which was over 3 and down 2, I believe. Sorry, where's my origin? Right there. Over 1, 2, 3, and down 1, 2. If I start actually right there, you have to actually be able to get there. Let me graph it again. If I start from the origin, there you go. It was 3, negative 2, right? Sorry, let me double check. Yeah, 3, negative 2. If I go over 1, 2, 3, down 1, 2, if I start right there, apparently you have to be more precise at clicking than I am because I can't seem to get it. But you would.
Is it at 1.5? I think go over 3 more spaces.
Oh, am I going? Wow, how am I blowing? No, I think I'm at 1.5 and negative. So I could try going over. Let's try going over to 3, actual 3, negative 2. I don't know. Sometimes I'm not great at clicking on things. I feel like it shouldn't be that hard though. It's also not the point. Right, so there you can see it from there. So if I start right there, I end up going to the origin. But anywhere else not on that eigenline diverges away from the origin because it's unstable, except if I travel along this path. And that's the path that corresponds to the negative eigenvalues. So I would encourage you to associate in your mind negative eigenvalues with stability and positive eigenvalues with instability. There was one last thing I wanted to say. Oh yeah, and Grant says that here. Like he says, if we started with the initial condition, x1 equals 3 and x2 equals negative 2, which is being on the eigenvector, right? x1 is 3, x2 is negative 2, that's right there. We end up on that line. And yeah, that's all I want to say. Okay, so where are we going with this? Well, actually, let me see. I feel like there's more I wanted to say here. Not you. Yeah, sorry, I thought there was another. I guess not. So we'll talk more about this next time, I guess, but that's kind of the idea, is that basically you don't have to find the general solution to know what's going to happen with the stability. All you have to look at is the eigenvalues, which is kind of nice. You don't even need to know what the eigenvectors are. So depending on which way your teachers go, that's a very likely way that we'll talk about. Like, oh yeah, if you want to classify whether an equilibrium is stable or unstable, you just look at the eigenvalues. Now, what's going to be the interesting twist? So I should say these eigenvalues that are real, they're either positive or negative. you get either, right, you get a saddle if they're opposite signs, you get a source if they're positive, you get a sink if they're negative. But then we're also going to look at imaginary or complex eigenvalues. And we're going to have a similar classification, but slightly different. So we're still going to see that if things are positive, we have instability, and if things are negative, we have stability. But it's not going to be a source or a sink. There's going to be some circulation or spiraling also if they are complex. And we'll talk about that on Friday. I think I'll end it there. I will post those quiz solutions and I will grade your quizzes. And please let me know if you guys have any questions. Once again, there's the thing, do the thing, and we'll talk to you guys on Friday. Take care.
Thank you.
You're welcome.